Okay, let's forget about dusty textbooks and, those impossible-looking equations for just a minute. Calculus isn't just some abstract math. It's like a secret language for describing a world that is always, and I mean always, changing. So today, we're going to learn the basics of that language and in the process, unlock a genuine superpower, the ability to find the absolute best solution to almost any problem. So here's our game plan. We're going to start with a pretty simple puzzle about a speeding car. From there, we'll uncover a secret hidden inside graphs, then build what I like to call a gradient machine to exploit it. And finally, we'll use that machine to solve a classic engineering problem. Trust me, by the end of this, you're going to see the world just a little bit differently. All right, first things first, time to put on your detective hat. We've got a situation on our hands, and we need to figure out if somebody actually broke the law. Okay, here's the case file. The journey is 2 kilometers long. The time it took was exactly 2 minutes and 40 seconds. And the speed limit? It's a strict 30 miles per hour. So based on just this information, can we write a ticket? Were they speeding?
Now, if you actually punch the numbers into a calculator, their average speed for the whole trip comes out to just under 28 miles per hour. So, case closed, right? I mean, they're under the limit? Well, not so fast.
See, the thing is, average speed is kind of misleading because nobody drives at one perfectly constant speed. You speed up, you slow down, you stop for a light, you know how it is. So the real question isn't about the average, it's about the instantaneous speed. At any single moment, did the needle on that speedometer ever creep past 30? To figure that out, we need a totally new way of looking at the problem. And that new way is to turn this whole problem into a picture. This is where the big central idea of calculus starts to show itself. And honestly, it's way more simple and visual than you might think. So check this out. If you plot a graph of distance traveled over time, speed suddenly has a visual identity. It's just the steepness of the line. A gentle, lazy slope means you're going slow, not covering much distance over time. But a really steep slope? Well, that means you're covering a lot of ground in a short amount of time. You're going fast. So this fancy term, rate of change, is really just another way of saying steepness or gradient. And this is where it gets incredibly powerful. This idea isn't just for cars, not by a long shot. We can use the exact same concept to see how quickly unemployment is rising, or how fast the temperature drops when you climb a mountain. We can even use it to predict how fast a population is growing. Basically, anything that changes has a slope we can analyze. But, okay, here's the catch. The real world doesn't usually give us nice straight lines. It gives us curves. And the steepness of a curve, well, it's changing constantly. It's different at every single point. So how in the world can we measure the exact steepness, the exact speed, at one specific instant in time? This is the exact problem that geniuses like Isaac Newton and Gottfried Leibniz tackled centuries ago. They created a mathematical tool to do just this. And for our purposes, we're going to call it the gradient machine. So this machine's official name is the derivative. And here's how it works. You feed it a function, which is just a recipe that describes a curve, and it spits out a brand new function. And this new function is the magic part. It can tell you the exact gradient, the precise instantaneous rate of change at any point you want on the original curve. And the best part? The engine of this machine runs on a surprisingly simple pattern. It's called the power rule. For any term like x to the power of n, its derivative is just n times x to the power of n minus 1. You just bring the power down in front as a multiplier, and then you subtract 1 from the original power. That's it. That little trick is the key to finding the slope of almost any curve you can think of. Okay, so we have this amazing machine that can tell us the rate of change anywhere on a curve. What's the big deal? What can we do with it? Well, this is where we unlock the superpower I was talking about, finding the absolute best possible outcome. I want you to picture the very top of a hill, or the very bottom of a valley on a graph. Right at that peak, for just a single brief moment, the curve is perfectly flat. It's not going up anymore, but it hasn't started going down yet. At that one instant, the peak, the minimum, the tipping point, the steepness, the rate of change is exactly 0. This is the secret key that unlocks everything. It's the core of optimization. If we want to find the absolute highest point, the maximum, or the absolute lowest point, the minimum, all we have to do is use our gradient machine to find the exact spot where the slope is 0. All right, enough theory. Let's get our hands dirty and put this superpower to work on a real-world problem. We're going to build the perfect box. So here's the challenge.
We've got a square piece of cardboard, 20 centimeters by 20 centimeters. We're going to snip identical squares out of each corner and then fold up the sides to make a box. Now, if we cut tiny squares, we get a really wide, shallow box. If we cut huge squares, we get a tall, skinny one. Somewhere in the middle, there's a perfect cut that gives us the biggest possible volume. How do we find it? Here's our 5-step plan of attack. First, we state our goal. Find the size of the cut, which we'll call X, that maximizes the volume. Second, we write a formula for that volume based on X. Third, we feed that formula into our gradient machine to get its derivative. That's the function that tells us its slope. Fourth, we find that tipping point by setting our new slope function equal to 0. And finally, we just solve for X. That's it. That'll give us the perfect cut. And when we follow those steps, the math doesn't give us a guess. It gives us a single, perfect answer. The ideal cut is about 3.33 centimeters, and making that one specific cut gives us the biggest possible volume we can get, which is 592.6 cubic centimeters. No trial and error, no guesswork. Calculus just hands us the one definitive, optimal solution. It's amazing. So let's just zoom out for a second and look at the journey we've just been on. Remember, this whole thing started with a simple question about a car. We discovered that this idea of a rate of change is really just something we can see. It's the steepness of a graph. We learned about the derivative, this incredible tool for measuring that steepness at any point. And most importantly, we found the secret key. Wherever that steepness hits 0, you find a tipping point, an absolute maximum or minimum. And that, right there, is the tool that lets us find the best of anything. And really, that's the heart of differential calculus. It's not about memorizing symbols. It's a powerful language for describing motion and growth and change. It's a toolkit for finding the single best way to do something, whether you're building a box, designing a shipping route, or modeling a financial market. So I guess the big takeaway is that this way of thinking can be applied, well, just about everywhere. So think about it. What is something in your work or even in your life that you're trying to maximize or minimize? What would it look like for you to find its tipping point?